All right, welcome back, friends and neighbors. It's time now for part 3. In the previous couple of videos, we worked through the RFCs. We talked about sort of how we got here and some of the lessons learned and problems experienced by the folks writing the RFCs. And then we did a little bit of review. But now it's time to actually work through a topology and see how this aggregation thing actually works. So if we remember, this was what the topology looked like. We've got a bunch of routers and a bunch of host-based networks out there that we got to provide addressing from. And all of this was supposed to fit inside one Class C network. And then, of course, we had to cleverly figure out how to aggregate all of the subnets back together. So if we remember some of the features, we had 9 routers, and altogether we had 18 networks. The 18 networks created the problem for us that it was not a power of 2. And so how do we decide how to break up our address space? How many subnets do we create? Things like that. We had lots and lots of stub networks, right? Those are our sort of cul-de-sacs in the networking world. They're the ones that you see down there below R6, R7, R8, R9, and on the left side of R1 and on the right side of R2. They're pretty obvious. Default gateway is the only way in or out. And then we got a bunch of point-to-point links, and the point-to-point links have no host on them whatsoever. So we're going to try and figure out what to do about all those things. Well, how do we start this whole thing? Well, one way to start, and sort of the requirement that I gave a bunch of my students, was to say, all right, let's just give each routed interface a network. Now, on the point-to-point links, obviously you'll have 2 routed interfaces on the same network, but the idea is that we'll just say, well, we'll just provide a whole bunch of networks out there, and we'll just fill in all the blanks. So we have 18 networks, and we'll just create 18 subnets. If we're doing this with a Class C, which we are in this example, it doesn't really work out, because if we wanted to create 18 networks, again, that's not a power of 2, and so what we have to do is create more networks than we actually wanted to, and that's going to be a problem for us. And we'll have to figure out what to do about that. We'll see how that works in a little bit. But just as a reminder, if you are stealing bits, every time you steal bits, you go up by a power of 2. So if we steal 1 bit, that's 2 subnets that we're going to create. If we steal 2 bits, that's 4 subnets. If we steal 3, that's 8, and so on and so forth. Now, the other thing to remember about this is that we're talking about a Class C, and so it doesn't really make any sense to steal 8 bits. But if we were talking about a Class A or a Class B network, then we might have a situation where we might actually be stealing 8 or even more bits. For example, RIT does 9-bit subnetting. So we create 512 subnets in that case. In those cases, you can actually create lots and lots and lots of subnets, far more than you would create if you were subnetting in a Class C. All right, so how would we assign the addresses here, right? So we've said, well, we're going to create 18 subnets, and we're going to make them all the same size. So how would we start assigning addresses? Well, it's very tempting to go right along the bottom and say, oh, those are all my host spaces, so I'll make sure that I give them addressing, and so we just follow the red arrows there. Well, we'll give the first subnet to the one below R6, and the second subnet to the other one below R6, and so on and so forth, just moving all the way to the right. And then we would just go up to the next layer up, and then we just assign the subnets along the way. And numerically that works out, and it looks very nice on paper, but it's just simply the wrong way to go. RFC 4623 gives us some very clear guidance on this, and in fact the other RFCs that were prior to 4623 do the same thing. You've got to assign your addresses along topological lines. So on paper you figure out what a subnet or aggregate together, and then after you do that, you follow your topological lines, and that's how you assign things. So there's another better way to do this that actually allows our routing to work. So if we take a look at this topology and we just sort of step back a little bit here and we say, well, there's actually some groupings that make sense. So if you were going to put your pen on the paper and just sort of trace the lines that we were flowing through, there are some things that make sense. The networks attached to R7, for example, it makes sense that they might actually be able to be aggregated together. Same thing with R6, R8, and R9. But then if we take a look, there's actually broader groups that might go together. R4 and R5 have big groups of networks that might work to aggregate together. And of course, the whole topology can be divided very nicely right in half. Now, you might have other networks that can be divided into thirds, into fourths, into fifths, whatever it is. But in this case, we've got a couple of very nice breakpoints. Still don't have an even number of routes, or a number of routes that are a power of 2. So we still got to figure that out. But we see these nice groupings that we can make use of. So we still have to be clever. We know that we need 32 subnets. And we could, as I said, just assign them all over the place. In this case, when you have 32 subnets, each one of those subnets is going to have 8 addresses associated with it, 6 usable after we get rid of the subnet ID and then the broadcast for the subnet. But if we were able to subnet 8 of these together, what that would mean is that we had 64 possible host addresses that might go together. Now, 8 is really close to this 9 number that we would have on one side. So if we divided the topology in half, we have 9 on one side and 9 on the other. 8 gets us really, really close. And so is there a way that we might be able to aggregate those together? Well, if we take a look at R4 and R5, that might actually work for us. And so if we said, well, I'm going to assign /29s and I'm clever about how I do it, I might be able to aggregate at those particular points. And so it turns out that if you aggregate 8 of those subnets together, they're collected together into a /26. And so if we take a look at the routing table that I provided for R3 here, you would have those 2 directly connected networks that are /29s. And then all of the other ones would be static routes, all via R4 or R5. And all of those could be aggregated together into /26s. So instead of having 18 routing table entries on R3, we might be able to get away with just 4. I said we got to be clever. So how are we going to actually do this? Well, there's a really good tip that you can follow. If you're creating routes on a router and you notice that the forwarding router interface is the same for a bunch of them, there's a really good chance they might be able to be summarized together or aggregated together. And so on the right-hand side here, I've sort of created a table of some of the networks that might be put together. Now, that /26 that I was talking about, there's only 4 of those in this class C. So the .0, the .64, the .128, and the .192. And so if we took 2 of those and we said, well, we got the .128 and the .192, all of those other /29s would be aggregated into those 2 /26s. So if we pick 2 of them, now I could have picked any 2 of them, I just grabbed the top 2. That takes care of our /26s that we're going to use for our static routes. We still have to come up with the directly connected routes, and so we'll see how that works in a second. Okay, so hold on a sec. We're actually advanced networking people, right? So maybe there's a better way to do this. Because when we put these routes together, right, we could just say, oh, all 8 of those, they're that way, and there's 8 more that are that way. But there's actually a much better way to do this when we're actually assigning them downstream. We notice that a couple of /29s can be put together into a /28. So if that's the case, then if we put /29s together on the same router, we can actually aggregate them together at one of the other routers. So we don't want to just consider things from the perspective of R3. We also want to consider things from the perspective of the other routers. So /28 gives us 2 /29s and so on. And so a whole bunch of those groupings down there below on the lower part of the networks. The /27 also gives us 4 of the /29s or 2 of the /28. So we got to make use of these ideas. Again, you're not thinking about this from the perspective of one router. You're thinking about this from the perspective of all the routers. How can we shorten up all of their routing tables and assign network address space in a way that makes sense? Okay, so if we just start along the bottom there and we see that .128 and .136 are together, they're 2 /29s. They can be aggregated into a /28. Same thing with 160 and 168, 192 and 200, 224 and 232. So at R4, we could actually collapse those routed interfaces into a single aggregated space. Okay, so these are two other sets of networks that can be aggregated together across the board. So we're not just thinking about R3, we're thinking about R4 and R5. So all of the address space here on the right side and on the left side can all be aggregated together in those /26s, and then downstream we can use /28s. And everybody else is using /29s for all the directly connected stuff. That still doesn't solve the problem of the two directly connected routes to R3 though. So R3, what we decided to do is use the .0/29 and the .8/29. And notice that those are outside of the address space chunks that we aggregated together. Okay, so that's a possible solution. And so if you're going to look at the commands and the routing tables that are actually generated as a result of this, we can see that if we're not doing aggregation, that's all the commands that I would have had to give on the router. Those are all the directly connected routes, and I just made the two neighboring routers, .1 and .2. And then we can see that the routing table would have all of those static routes in there, and they're all from the same address space. Now, on the other hand, I could get rid of all of those IP route statements and all of those static routes in the routing table and replace all those commands with one IP route command that you see on the top right. And that is just the aggregated collection of routes. And you can see the change in the mask in the second field. And then, of course, you see the change in the routing table. We're now down from all 8 of those plus the 2 directly connected to the 2 directly connected and then one single aggregated route. So that might be a way to go. Sounds pretty good so far, right? We all done? We're going to call it a day on this problem? Nope. Well, this got the job done, and it actually works, and it allows us to do some aggregation and feel pretty clever about things, especially when we consider that we were able to do things on R4 and R5. It's still pretty doggone wasteful as far as address space goes. For example, on the point-to-point links, we're using 8 addresses on those when we really only need 4 or even 2 addresses, and we'll see how that works in a little bit. We might even have a couple of other tricks up our sleeve to recover some more space. Well, hopefully you got something out of that aggregation video, and that's our example of how we could create an addressing scheme that would work, although it's a little bit wasteful. Next up, we'll see if we can improve things on this aggregation odyssey. Thanks for watching, thanks for listening, and may your packets always reach their destinations.